The topic of my lecture is symbolic logic. This slide gives an overview of the syllabus. Here my lecture is centered around moreover Unit 2 and Unit 3. Some aspects of Unit 1 have been covered, and also to an extent Unit 4. So it is necessary to go through the study material also. What is logic?
Logic is actually the method and principles in evaluating good reasoning from bad reasoning or correct reasoning from incorrect reasoning. Logic is considered the basic science of sciences. Since correct reasoning is the basis of scientific study in any field, logic is concerned with norms to distinguish between correct and incorrect reasoning. Study of logic will help students to get the technique and methods to test different kinds of reasoning, including one's own. When errors are easily detected, they are less likely to be made. It does not mean that a person who has studied logic can only reason correctly, but if two persons of the same intellect, one trained in logic, will reason properly than other who has not thought about the general principles involved in it. So this slide will give a general idea about what is logic.
Before we understand nature of an argument, we have to understand the meaning of certain basic terms like inference, premises, and conclusion. So inferring എന്ന് പറയുന്നത് is an activity by which one proposition is affirmed on the basis of one or more other propositions that are accepted as starting points of the process. And നമ്മൾ propositions എന്ന് പറയുമ്പോൾ എന്താണ്? Propositions are either true or false. That they differ from questions, commands, and exclamations. Propositions എന്ന് പറയുന്നത് is sentence എന്ന് പറയുന്നത് always part of the language, and whereas propositions are not peculiar to any language. അതാണ് അതിൻ്റെ ഒരു main difference. അപ്പോൾ only propositions can be affirmed or denied. Nature of an argument. An argument in logician sense is any group of propositions of which one is set claimed to follow from others, which are regarded as providing support for grounds of truth of that one. അപ്പോൾ ഇതാണ് ഒരു ആർഗ്യുമെൻ്റ്. ഒരു ലൊജീഷ്യൻ്റെ സെൻസിൽ എന്താണ് ഒരു ആർഗ്യുമെൻ്റ് എന്നുള്ള ഡെഫിനിഷനാണ് ഈ പറഞ്ഞിട്ടുള്ളത്. In describing the structure of an argument, the terms premise and conclusion are used. The conclusion of an argument is a proposition which is affirmed on the basis of other propositions of the argument. These other propositions which provide support or provide reason for accepting the conclusion are called premises. ഇവിടെ ഞാൻ ഒരു എക്സാമ്പിൾ പറഞ്ഞിട്ടുണ്ട്. All men are mortal. Socrates is a man, therefore Socrates is mortal. അപ്പോൾ ഇതിൻ്റെ അകത്ത് premises എന്ന് പറയുന്നത് all men are mortal, Socrates is a man. ഇത് രണ്ടും premise ആണ്. അതിൻ്റെ conclusion എന്ന് പറയുന്നത് Socrates is mortal. Now coming to deduction and induction. അപ്പോൾ ആർഗ്യുമെൻസിനെ നമുക്ക് രണ്ട് രീതിയിൽ വേർതിരിക്കാം. ഒന്ന് ഡിഡക്ഷൻ, ഒന്ന് ഇൻഡക്ഷൻ, അല്ലെങ്കിൽ ഡിഡക്റ്റീവ് ലോജിക് ആൻഡ് ഇൻഡക്റ്റീവ് ലോജിക്. അപ്പോൾ എന്താണ് ഒരു ഡിഡക്റ്റീവ് ആർഗ്യുമെൻറ്റിൻ്റെ ഡെഫിനിഷൻ എന്ന് നമുക്ക് നോക്കാം. ഡിഡക്റ്റീവ് ആർഗ്യുമെൻറ്റ് ഇൻവോൾവ്സ് എ ക്ലെയിം ദാറ്റ് ഇറ്റ്സ് premises provide conclusive grounds for the truth of its conclusion. ഇവിടെയാണ് നമ്മൾ ശ്രദ്ധിക്കേണ്ടത്. ദാറ്റ് ഈസ് ഇറ്റ്സ് premises provide conclusive grounds for the truth of its conclusion. When the reasoning in a deductive argument is correct, we call the argument valid. Inductive argument involves the claim that its premise provides some support for the truth of its conclusion. പക്ഷേ ഇൻഡക്റ്റീവ് ആർഗ്യുമെൻ്റ് എന്ന് എൻ്റെ ഡെഫിനിഷനിൽ പറയണ ഇൻഡക്റ്റീവ് ആർഗ്യുമെൻ്റ് ഇൻവോൾവ്സ് ദ ക്ലെയിം ദാറ്റ് ഇറ്റ്സ് premise provides some support for the truth of its conclusion. ഇനി നമുക്ക് എന്താ ഡിഡക്റ്റീവ് ലോജിക് നോക്കാം. In the realm of deductive logic, the central task is to clarify the relation between premises and conclusion in valid arguments and allow us to distinguish between valid and invalid arguments. If a deductive argument is valid, then given the truth of the premises, its conclusion must be true also. An example for deductive argument would be, ഇവിടെയും അതേ സെയിം എക്സാമ്പിൾ തന്നെ ഉപയോഗിക്കുകയാണ്. ദാറ്റ് ഈസ് ഓൾ മെൻ ആർ മോർട്ടൽ, സോക്രട്ടീസ് ഈസ് എ മാൻ, ദെർഫോർ സോക്രട്ടീസ് ഈസ് മോർട്ടൽ. ഇതൊരു ഡിഡക്റ്റീവ് ലോജിക്കിൻ്റെ ഒരു എക്സാമ്പിളാണ്, അല്ലെങ്കിൽ ഡിഡക്ഷൻ്റെ ഒരു എക്സാമ്പിളാണ്. എന്താ ഇൻഡക്ഷൻ നോക്കാം. A is an elephant has 4 legs, B is an elephant has 4 legs, C is an elephant has 4 legs. അതുകൊണ്ട് നമുക്ക് കൺക്ലൂഡ് ചെയ്യാൻ പറ്റും all elephants have 4 legs. ഒരു ഇൻവാലിഡ് ആർഗ്യുമെൻറ്റിൻ്റെ എക്സാമ്പിൾ ഇവിടെ കൊടുത്തേക്കണം. ഓൾ മാമൽസ് ഹാവ് വിങ്സ്, ഓൾ വെയിൽസ് ഹാവ് വിങ്സ്, therefore all mammals are whales. The above argument is invalid. Here all the premises and the conclusion is false. നമുക്ക് വേറൊരു എക്സാമ്പിളിലേക്ക് പോവാം. All trouts are mammals, all mammals have wings, therefore all trouts have wings. In the above argument, all the premises and the conclusion is false, yet the argument is valid. It means the validity of an argument does not guarantee the truth of its conclusion. Let us have a look at another example. If I am the president, then I am famous. I am not the president, therefore I am not famous. ഇതിൻ്റെ അകത്തുള്ള പ്രമിസുകളും കൺക്ലൂഷൻ നോക്കുകയാണെങ്കിൽ നമുക്ക് മനസ്സിലാക്കാം, ഈ എല്ലാ പ്രപ്പോസിഷൻസും ട്രൂ ആണ്. പക്ഷേ the argument is still invalid. Instead of I, that is, ഇപ്പോൾ നമ്മൾ ഈ ഒരു ഓൾറെഡി ഫേമസ് ആയിട്ടുള്ളൊരു പേഴ്സണാലിറ്റിയുടെ പേര് ഇവിടെ വയ്ക്കുകയാണെങ്കിൽ the conclusion will become false. അപ്പോൾ രണ്ട് ട്രൂ പ്രമിസും ഒരു കൺക്ലൂഷൻ ഫോൾസ് ആകുമ്പോൾ ഓട്ടോമാറ്റിക്കലി the argument will become invalid. I will just read what is written down here. Though here the premises and the conclusion is true, still the argument is invalid. Instead of I, if we add the name of any famous personality in the above argument, then the conclusion will become false. Falsehood of the conclusion does not guarantee the invalidity of the argument, but falsehood of the conclusion does guarantee that either the argument is invalid or at least one of its premise is false. Categorical prepositions either affirms or denies something about a class of things unconditionally. The main characteristics are, it is always in indicative mode, it is always in present tense, and the copula must be separate from the subject and object. Distribution of terms. When a certain attribute is predicated to the whole of the subject term, the subject is said to be distributed. If only a part of it is referred to, then the term is characterized as undistributed. In universal propositions, the subject term is distributed, and in particular propositions, the subject term is undistributed. In affirmative propositions, predicate term is undistributed, while in negative propositions the predicate term is distributed. 4 types of categorical prepositions. A proposition, which is called universal affirmative, all S is P. E proposition, which is called universal negative, no S is P. O proposition, which is a particular affirmative, some S is P. I proposition, which is a particular negative, some S is not P. The term about which affirmation or denial is made the subject. The term which is affirmed or denied is the predicate. The connecting link is the copula. The truth relation between various categorical prepositions A, E, I, O. These relations are termed oppositions. Traditional logicians have explained by means of a diagram called square of opposition, which is as given below. Coming to what is a categorical syllogism. Any deductive argument in which the conclusion is drawn from two premises is a syllogism. It is the mediate inference in which two premises jointly imply the conclusion. In the categorical syllogism, all propositions are categorical. An example is given here. All planets revolve around the sun. Venus is a planet, therefore Venus revolves around the sun. It is the position of the middle term which determines the figure of syllogism. The following slide gives the four different figures. So after covering truth and validity, I am directly coming to the title of the paper, that is Symbolic Logic. And since the emphasis of the whole of the paper is on symbolic logic, I am currently going to discuss symbolic logic. So from the previous discussion, it is known that the concern of logic is arguments, and arguments contain proposition as their premises and conclusion. So communication of arguments and propositions requires the use of language. Arguments, when put in natural language, is usually difficult for the logician to verify its validity due to the vague and equivocal nature of words in which they are expressed. So നമ്മളിപ്പോൾ ഇവിടെ എന്താ ശ്രദ്ധിക്കണമെന്ന് വെച്ചാൽ ഈ ആർഗ്യുമെൻറ്റ്സ് നമ്മൾ നാച്ചുറൽ ലാംഗ്വേജിലായിരിക്കും നമ്മൾ എഴുതുന്നത്. അപ്പോൾ അതുകൊണ്ട് തന്നെ ഒരു ലൊജീഷ്യനെ സംബന്ധിച്ച് അതിൻ്റെ വാലിഡിറ്റി കണ്ടെത്താൻ അത്ര എളുപ്പമായിരിക്കില്ല. എന്തുകൊണ്ടാണെന്ന് വെച്ചാൽ അതിൻ്റെ അകത്ത് വേഗ്നെസ്സും വേർഡ്സിൻ്റെ ഇക്വിവോക്കൽ നേച്ചർ ഉണ്ടാവുമ്പോൾ അത് ലൊജീഷ്യൻ അതിൻ്റെ വാലിഡിറ്റി കണ്ടെത്താൻ ബുദ്ധിമുട്ടായിരിക്കും. സോ ആ ആംബിഗ്വിറ്റി മാറ്റാൻ വേണ്ടി also the ambiguity in the construction and the idioms that they may contain will pose peripheral difficulties. So ആ പെരിഫറൽ ഡിഫിക്കൽട്ടീസ് മാറ്റാൻ ലൊജീഷ്യൻ എന്താ ചെയ്യണേ? അപ്പോൾ അതിനുവേണ്ടി വേരിയസ് സയൻസസ് ഹാവ് ഡെവലപ്ഡ് സ്പെഷ്യലൈസ്ഡ് ടെക്നിക്കൽ വൊക്കാബുലറീസ്. അപ്പോൾ ഒരു സയൻറ്റിസ്റ്റ് യൂസസ് ദീസ് ടെക്നിക്കൽ വൊക്കാബുലറീസ് ഇൻ എ വേ ദാറ്റ് ഇറ്റ് ഈസ് എക്കോണമിക്കൽ. The space and time required for writing theories and reports are reduced by special symbols, which otherwise requires long sequence of familiar words to communicate. അപ്പോൾ ഈ ടെക്നിക്കൽ വൊക്കാബുലറീസ് ഉപയോഗിക്കുന്നത് കൊണ്ട് സയൻറ്റിസ്റ്റിന് എങ്ങനെയാണോ ഒരുപാട് സമയം ലാഭിക്കാനും പറ്റും, അതേപോലെ സ്പേസ് ആൻഡ് ടൈം റിക്വയർഡ് ഫോർ ദ റൈറ്റിംഗ് തിയറീസ് ആൻഡ് റിപ്പോർട്ട്സ് ആർ റെഡ്യൂസ്ഡ് ബൈ യൂസിങ് സ്പെഷ്യൽ സിമ്പിൾസ്. അപ്പോൾ അതേപോലെ തന്നെ ലൊജീഷ്യൻസും സ്പെഷ്യൽ സിമ്പിൾസ് ഉപയോഗിക്കും. അപ്പോൾ ഫോർ എക്സാമ്പിൾ നമ്മൾ മാത്സിൽ ഇപ്പോൾ പി ഇൻറ്റു പി ഇൻറ്റു പി ഇൻറ്റു പി ഇൻറ്റു പി ഈസ് ഈക്വൽ ടു ക്യൂ ഇൻറ്റു ക്യൂ ഇൻറ്റു ക്യൂ എന്ന് പറയുന്നതിന് വരും. പി റേസ് ടു 5 ഈസ് ഈക്വൽ ടു ക്യൂ റേസ് ടു 3 എന്ന് എഴുതുമ്പോൾ ദാറ്റ് ഈസ് ഈസിയർ. അപ്പോൾ ലാംഗ്വേജ് ഓഫ് എവറി സയൻസ് ഹാസ് സിമിലർ സിംബോളിക് ഇന്നോവേഷൻസ്. സോ സ്പെഷ്യൽ നൊട്ടേഷൻസ് ഹാവ് ബീൻ ഡെവലപ്ഡ് ഫോർ ലോജിക് ഓൾസോ. അതുകൊണ്ട് തന്നെ ലോജിക്കിൽ ഇങ്ങനെ സ്പെഷ്യൽ നൊട്ടേഷൻസ് ഡെവലപ്പ് ചെയ്തിട്ടുണ്ട്. Even Aristotle used certain abbreviation. The modern symbolic logic introduced many special symbols. അപ്പോൾ modern symbolic logic അതുപോലെ കുറേ special symbols ഉണ്ടാക്കിയിട്ടുണ്ട്. The difference between old and new logic is only of degrees rather than kind, but the difference in degree is tremendous. There will be better clarity to the logical structure of arguments by using the special symbols of symbolic logic. അതുകൊണ്ട് തന്നെ ഈ ലോജിക്കൽ സ്ട്രക്ചർ ഓഫ് ആർഗ്യുമെൻറ്റ്സിന് ക്ലാരിറ്റി ഉണ്ടാവാൻ ഈ സ്പെഷ്യൽ സിമ്പിൾസ് ഉപയോഗിക്കാം. ഇറ്റ് മേക്സ് ഇറ്റ് ഈസിയർ ടു ഡിവൈഡ് ആർഗ്യുമെൻറ്റ്സ് ഇൻറ്റു വാലിഡ് ആൻഡ് ഇൻവാലിഡ് ബൈ യൂസിങ് സ്പെഷ്യൽ സിമ്പിൾസ്. നമുക്ക് ആദ്യം തന്നെ ലെറ്റ് us look at ആർഗ്യുമെൻറ്റ്സ് കണ്ടെയ്നിങ് കോമ്പൗണ്ട് സ്റ്റേറ്റ്മെൻറ്റ്സ്. അപ്പോൾ എന്താണ് സിമ്പിൾ സ്റ്റേറ്റ്മെൻറ്റ്സ്, എന്താണ് കോമ്പൗണ്ട് സ്റ്റേറ്റ്മെൻറ്റ് എന്നൊക്കെ നമുക്ക് നോക്കാം. സ്റ്റേറ്റ്മെൻറ്റ്സ് ആർ of two kinds, simple and compound. A simple statement is one that does not contain any other statement as its component, whereas every compound statement does contain another statement as its component part. അത് സിമ്പിളാണ്, മനസ്സിലാക്കാൻ എളുപ്പമാണ്. ദാറ്റ് ഈസ് ഒരു എക്സാമ്പിൾ പറയുകയാണെങ്കിൽ റോസസ് ആർ റെഡ് ആൻഡ് വയലറ്റ്സ് ആർ ബ്ലൂ. അപ്പോൾ ഇവിടെ രണ്ട്
സിമ്പിൾ സ്റ്റേറ്റ്മെൻറ്റ്സ് ഉണ്ട്. റോസസ് ആർ റെഡും വയലറ്റ്സ് ആർ ബ്ലൂ. അപ്പോൾ ഇത് രണ്ടും കൂടി ചേർക്കുമ്പോൾ അതൊരു കൺജങ്ഷൻ എന്നാണ് പറയുന്നത്. ദ എബോവ് സ്റ്റേറ്റ്മെൻറ്റ് ഈസ് എ കൺജങ്ഷൻ. ദ കൺജങ്ഷൻ ഈസ് ഫോൺ ബൈ ഇൻസേർട്ടിങ് എ വേർഡ് ആൻഡ് ബിറ്റ്വീൻ ഇറ്റ്. രാമു ആൻഡ് രാജു ആർ ബ്രദേഴ്സ്. ഇപ്പോൾ രണ്ടാമത്തേൽ ഞാൻ പറയുമ്പോൾ രാമു ആൻഡ് രാജു ആർ ബ്രദേഴ്സ് എന്ന് പറയുമ്പോൾ ഈ ഇവിടെ ആൻഡ് ഉപയോഗിക്കുന്ന വേറെ സെൻസിലാണ്. അപ്പോൾ നേരത്തെ നമ്മൾ റോസസ് ആർ റെഡ് ആൻഡ് വയലറ്റ്സ് ആർ ബ്ലൂ എന്ന് പോലെയല്ല താഴത്ത് നമ്മൾ ആൻഡ് ഉപയോഗിക്കുന്നത്. അപ്പോൾ അത് നമ്മൾ ശ്രദ്ധിക്കണം. ദാറ്റ് ഈസ് എ കൺജങ്ഷൻ എന്ന് പറയുമ്പോൾ ഇങ്ങനെയാണ്: റോസസ് ആർ റെഡ് ആൻഡ് വയലറ്റ്സ് ആർ ബ്ലൂ. The truth value of the compound statement is determined by the truth value of the conjuncts. In the above statement, roses are red and violets are blue are conjuncts. അപ്പോൾ ഇവരെ ഈ റോസസ് ആർ റെഡും വയലറ്റ്സ് ആർ ബ്ലൂവും നമ്മൾ കൺജങ്ക്സ് എന്നാണ് പറയുന്നത്. ഇനി അടുത്തത് ട്രൂത്ത് വാല്യൂ ഓഫ് എ സ്റ്റേറ്റ്മെൻറ്റ്. എന്താണ് ട്രൂത്ത് വാല്യൂ ഓഫ് എ സ്റ്റേറ്റ്മെൻറ്റ്? അപ്പോൾ ഒരു ട്രൂത്ത് വാല്യൂ ഓഫ് എ ട്രൂത്ത് സ്റ്റേറ്റ്മെൻറ്റ് ഈസ് ട്രൂ, ട്രൂത്ത് വാല്യൂ ഓഫ് എ ഫോൾസ് സ്റ്റേറ്റ്മെൻറ്റ് ഈസ് ഫോൾസ്. അത് തന്നെ, അതാണ് അതിൻ്റെ ഒരു ഡെഫിനേഷൻ എന്ന് പറഞ്ഞാൽ. കൺജങ്ഷൻ ഈസ് ട്രൂത്ത് ഫങ്ഷണൽ കോമ്പൗണ്ട് സ്റ്റേറ്റ്മെൻറ്റ് ആൻഡ് ഇറ്റ്സ് കൺജങ്ക്സ് ആർ ട്രൂത്ത് ഫങ്ഷണൽ കോമ്പണൻസ് ഓഫ് ഇറ്റ്. കൺജങ്ഷൻ എന്ന് പറയുന്നത് ഈസ് എ ട്രൂത്ത് ഫങ്ഷണൽ കോമ്പൗണ്ട് സ്റ്റേറ്റ്മെൻ്റ് ആണ് ആൻഡ് ഇറ്റ്സ് കൺജങ്ക്സ് ആർ ട്രൂത്ത് ഫങ്ഷണൽ കോമ്പണൻസ് ഓഫ് ഇറ്റ്. Since conjunctions are truth functionally compound statement, the dot symbol is used as truth functional connective. അപ്പോൾ നമ്മൾ ആൻഡ് എന്നൊക്കെ വരുമ്പോൾ നമ്മൾ ഡോട്ട് സിമ്പിളാണ് ഉപയോഗിക്കുന്നത്. Other English words such as but, yet, still, however, also, nevertheless, although, and so forth, and even comma and semicolon are used to conjoin two statements into a single compound one, and all of them can be indifferently translated into the dot symbol so far as the truth values are concerned. Given any two statements P and Q, there are just four possible sets of truth values they can have. In every case, the truth value of their conjunction PQ is uniquely determined. The four possible cases can be exhibited as follows. അപ്പോൾ നമ്മൾ ഒരു ട്രൂത്ത് ടേബിൾ വരച്ചിട്ട് എങ്ങനെയാണ് ട്രൂത്ത് വാല്യൂ ഓഫ് കൺജങ്ഷന് നമുക്ക് ഡിസ്പ്ലേ ചെയ്യാൻ പറ്റുമെന്ന് നോക്കാം. അത് ഈ ടേബിൾ നോക്കിയാൽ മനസ്സിലാവും. ആദ്യത്തെ കോളം നോക്കിയാൽ പിൻ്റെ കോളമാണ്, രണ്ടാമത്തെ കോളം ക്യൂവിൻ്റെ കോളമാണ്, അതിൻ്റെ കൺജങ്ഷൻ മൂന്നാമത്തെ കോളം. എത്ര റോ ഉണ്ട് നോക്കിയേ? 1 2 3 4 റോ ഉണ്ട്. അപ്പോൾ 3 കോളവും 4 റോ ഉള്ളൊരു ടേബിളിൽ നമുക്ക് ഈ ഒരു കൺജങ്ഷൻ നമുക്ക് ഡിസ്പ്ലേ ചെയ്യാൻ പറ്റും. അപ്പോൾ അതിൻ്റെ മൂന്നാമത്തെ കോളം നോക്കിയാൽ പി ഡോട്ട് ക്യൂ എന്താ വരുന്നത്? ടി ആവുമ്പോൾ രണ്ടും ട്രൂ ആവുമ്പോൾ ദി കൺക്ലൂഷൻ ഈസ് ട്രൂ. ആദ്യത്തെ പ്രൊപ്പോസിഷൻ ട്രൂ ആണ്, രണ്ടാമത്തെ പ്രൊപ്പോസിഷൻ ഫോൾസ് ആവുമ്പോൾ ദി കൺജങ്ഷൻ ഈസ് ഫോൾസ്. ആദ്യത്തെ പ്രൊപ്പോസിഷൻ ഫോൾസ് ആവുമ്പോൾ രണ്ടാമത്തെ പ്രൊപ്പോസിഷൻ ട്രൂ ആവുമ്പോൾ ദ കൺജങ്ഷൻ ഈസ് അഗെയിൻ ഫോൾസ്. പിന്നെ രണ്ടും ഫോൾസ് ആവുമ്പോൾ കൺജങ്ഷൻ ഈസ് ഫോൾസ്. ഇനി നമുക്ക് എന്താ ഡിസ്റ്റിങ്ഷൻ നോക്കാം. അപ്പോൾ ഡിസ്റ്റിങ്ഷൻ ഉപയോഗിക്കുന്ന ഒരു സിമ്പലാണ് വെഡ്ജ് എന്ന് പറഞ്ഞിട്ട് വി, ഒരു ചെറിയ വി ഷേപ്പിൽ. The distinction formed by inserting the word V between them results in a compound statement. The two statements are called disjuncts. Truth value of disjuncts displayed by means of truth table. But here the symbol V uses inclusive sense of the word or it is called a wedge. ഇവിടെ ഒരു ഇൻക്ലൂസീവ് സെൻസിലാണ് ഓർ ഉപയോഗിച്ചേക്കുന്നത്. അപ്പോൾ അല്ലാതെ നമ്മൾ ടീ ഓർ കോഫി, വുഡ് യു പ്രിഫർ ടീ ഓർ കോഫി, അങ്ങനെ ഒരു സെൻസിലല്ല. Instead, it is an inclusive sense of the word or. അപ്പോൾ ഇവിടെ നമുക്ക് ട്രൂത്ത് ടേബിൾ ഡിസ്പ്ലേ ചെയ്തേക്കണം നോക്കാം. അപ്പോൾ അതിൻ്റെ അകത്ത് ആദ്യത്തെ കോളം പി ആണ്, രണ്ടാമത്തെ കോളം ക്യൂ ആണ്, മൂന്നാമത്തെ കോളം പി ഓർ ക്യൂ ആണ്. അപ്പോൾ അതിൻ്റെ എങ്ങനെയാണ് അതിൻ്റെ പ്രപ്പോസിഷൻ? ആദ്യത്തെ പ്രപ്പോസിഷൻ ടി ട്രൂ ആകുമ്പോൾ രണ്ടാമത്തെ പ്രപ്പോസിഷൻ ട്രൂ ആകുമ്പോൾ കൺക്ലൂഷൻ ട്രൂ ആണ്. അതേപോലെ ആദ്യത്തെ പ്രപ്പോസിഷൻ ട്രൂവും രണ്ടാമത്തെ പ്രപ്പോസിഷൻ ഫോൾസ് ആവുമ്പോൾ കൺക്ലൂഷൻ ട്രൂ ആണ്. ആദ്യത്തെ പ്രപ്പോസിഷൻ ഫോൾസ് ആവുമ്പോൾ രണ്ടാമത്തെ പ്രപ്പോസിഷൻ ട്രൂ ആവുമ്പോൾ മൂന്നാമത്തെ കൺക്ലൂഷൻ ട്രൂ ആണ്. അപ്പോൾ അതേപോലെ രണ്ടും ഫോൾസ് ആവുമ്പോൾ കൺക്ലൂഷൻ ഫോൾസ് ആണ്. നമുക്ക് എന്താ നിഗേഷൻ നോക്കാം. ഇപ്പോൾ നമ്മൾ പറയാം ഫുഡ് ഈസ് ഡെലീഷ്യസ്. അപ്പോൾ അതിൻ്റെ നെഗേഷൻ അത് പി ആയിട്ട് എടുക്കുകയാണെങ്കിൽ നെഗേഷൻ പി എന്ന് പറയുന്നത് ഇറ്റ് ഈസ് നോട്ട് ദ കേസ് ദാറ്റ് ഫുഡ് ഈസ് ഡിലീഷ്യസ്. അല്ലെങ്കിൽ എന്താണോ നമ്മൾ പറയുന്നത് അതിൻ്റെ നെഗേറ്റീവ് ആണ്. ഇപ്പോൾ പി ട്രൂ ആണെങ്കിൽ അതിനർത്ഥം നെഗേഷൻ പി ഫോൾസ് ആണ്. ഈ പി ഫോൾസ് ആണെങ്കിൽ അതിൻ്റെ നെഗേഷൻ പി ട്രൂ ആണ്. So like in mathematics, symbolic logic also uses parentheses, braces, brackets for punctuation. P dot Q or R എന്നുള്ളൊരു സ്റ്റേറ്റ്മെൻറ്റ് നമ്മൾ എങ്ങനെയാണ് നമ്മൾ ബ്രാക്കറ്റ് ഉപയോഗിക്കണമെന്ന് നോക്കാം. ബ്രാക്കറ്റ് ക്യാൻ ബി പ്ലേസ് ലൈക്ക് പി ഡോട്ട് ബ്രാക്കറ്റിൻ്റെ അത് പി ഡോട്ട് ക്യൂ ഓർ ആർ ഓർ പി ഡോട്ട് ക്യൂ ഓർ ആർ വിച്ച് ഹാവ് ഡിഫറെൻറ്റ് മീനിങ് വെൻ സിംബലൈസ്ഡ്. ഫോർ എക്സാമ്പിൾ നമുക്ക് രണ്ട് സ്റ്റേറ്റ്മെൻറ്റ് എടുക്കാം. ദാറ്റ് ഈസ് ജോൺ ആൻഡ് സ്മിത്ത് വിൽ നോട്ട് ബോത്ത് വിൻ ദ മാച്ച് നമ്മൾ സിംബലൈസ് ചെയ്യുമ്പോഴും ജോൺ ആൻഡ് സ്മിത്ത് വിൽ ബോത്ത് നോട്ട് വിൻ ദ മാച്ച് എന്ന് സിംബലൈസ് ചെയ്യുമ്പോഴും രണ്ട് രീതിയിലാണ് നമ്മളതിനെ സിംബലൈസ് ചെയ്യണത്. അതപ്പോൾ നമ്മൾ ദാറ്റ് വി ഷുഡ് ബി വെരി കെയർഫുൾ വെൻ സിംബലൈസിങ് such statements. So let us take an example. Suppose if P and Q is true and X and Y are false, then what will be the truth value of P or X dot Y? So here we can look, the statement given is P or X dot Y. So and what is defined is P and Q is true. So in this first problem, that is if we take P as true and X and Y as false, you can refer the truth table and check. That is, if X dot Y, for if X and Y are false, then what will be the conjunction of X and Y? It will be false. And if so, then we what will be the answer? The answer will be true, since P is true, the truth value, the truth value of the statement P or X dot Y will be true. So similarly, we take another example like P dot in the brackets X or Q dot Y. So similarly, if we check with the truth table, it will be we will find that the truth value of such a statement is false. So students can work out on more problems from their logic textbooks. Now how to symbolize? That is, I am given here is a statement, either Barcelona or Napoli will win the football match, but they will not both win the football match. How can it be symbolized? So first of all, we have to have in mind what is the abbreviation that we are going to use to symbolize a statement of such kind. That is, it is a club, Barcelona or Napoli, or how that is, first of all, we have to have in our mind an alphabet which will stand for the symbolization. Like if either Barcelona, we are taking B for symbolizing Barcelona and for Napoli, then then we should apply the rules of symbolic logic. Like first of all, the first statement is given, either Barcelona or Napoli will win the football match, then that is written as B or N, and in a bracket and conjunction the negation of B dot N. It is because it is here given that but they will not both win the football match. It is symbolized negation of B dot N. Coming to conditional statement. A conditional does not say that its antecedent is true or its consequent is true. It only says that if the antecedent is true, then the consequent is true also. Any conditional with true antecedent and false conclusion must be false. If P, then Q is known to be false in case P conjunction negation Q is true. For the conditional to be true, the indicated conjunction must be false, which means the negation of the conjunction must be true. We can symbolize it as negation of P conjunction negation Q is true.
If P then Q to be true, negation of the conjunction of P with the negation of Q should be true. The partial meaning that is common to all conditional statement is represented by a new symbol called horseshoe. What it means is that there is no real connection is alleged to hold between what the antecedent states and what is stated by the consequent. This sort of conditional is ordinarily intended as an emphatic or humorous method of denying the truth of its antecedent, for it typically contains a notoriously or ridiculously false statement as its consequent. So, from this truth table given here, we can understand the meaning of the new symbol or horseshoe. That is, it is equivalent to negation of P conjunction negation of Q. And as before in the truth table, if it is P is true and Q is true, then negation Q is false. P dot negation Q is false. Then a negation of P negation Q is then true. Similarly, in the next row, if P is true and Q is false, then negation Q is true. Then P conjunction negation Q is true. Then negation of that will be false. Then the next row, if P is false and Q is true, then negation Q is automatically false. Then P conjunction negation Q is false, and negation of P conjunction negation Q is true. And in the last column, if P is false, then Q is false, then negation Q is true and P conjunction negation Q is false, then the negation of P conjunction negation Q is true. So we can see that in this only in the second row the now we can have a look at how we can symbolize the following statement, that if Barcelona does not win its first game, then it is not the case that either Napoli or Real Madrid wins its first game. So how can that is, first of all, we have to have in mind what we will use for abbreviation. So for Barcelona we use B, and for Napoli N, and for Real Madrid R. So we can symbolize it as negation B implies negation of N or R. So coming to argument forms and truth table. Any arguments, that is, we have gone through different arguments. That is, suppose example of a valid argument is all men are mortal, Socrates is a man, therefore Socrates is mortal. So and we have also gone through many arguments which are invalid. So any argument is proved to be invalid if another argument of exactly the same form can be constructed with true premises and false conclusion. So if we find any substitution instance in the truth table with true premises and false conclusion, then automatically that argument is invalid. This reflects the fact that validity and invalidity are purely formal characteristics of argument. So it is the formal characteristic of the argument. Any two arguments having the same form are either both valid or both invalid, regardless of any differences in their subject matter. So this is please keep in mind, this is an important thing that one should not forget. A student of logic should not forget. For convenience, we use PQRS as statement variables in the place of which statements could be substituted. Now, argument form is defined as an array of symbols that contain statement variables such that when statement is substituted in statement variables,
in which the same statement is being substituted for the occurrence of the same statement variable throughout. The terms valid and invalid can be extended to apply to argument forms as well as arguments. An invalid argument form is one that has at least one substitution instance with true premises and false conclusion. So valid argument form is one that has no substitution instance with true premises and false conclusion. Any given argument can be proved valid if it can be shown that the specific form of the given argument is a valid argument form. In order to verify the validity or invalidity of an argument form, one has to construct the truth table and verify all substitution instances to see if any of them have true premises and false conclusion. Let us have a look of how we can symbolize a statement. Electrical wiring should be insulated or there is chance of electrocution. Electrical wirings not insulated. So the conclusion will be there is chance of electrocution. So which can be symbolized as E or C, a negation E, therefore C. Or can be written using statement variables as P or Q, negation Q, therefore Q. So let us check the validity of the above argument using truth table. Here P and Q are the statement variables. So here P or Q is the first premise, negation P is the second premise, and Q is the conclusion. We can check with the premises and conclusion and look for any substitution instance with true premises and false conclusion. So we have not found any premises with any substitution instance with true premises and false conclusion. So the above argument is valid. Now coming to another argument form, that is a modest tolerance, which is written as P implies Q, negation P. So this is an argument form. We can check the validity of it using the truth table. Again, which are the premises? P implies Q is the first premise and negation Q is the second premise. So we are checking if there is any substitution instance with true premises and false conclusion. So we have found no such instance in which there is the premises are true and the conclusion is false. Hence, we can state that this argument form is valid. Now coming to tautology, a statement is a tautology if the column under its main connective is true on every row of a complete truth table. Now consider the statement, it is raining or no, it is not raining. It can be symbolized P or negation P. The tautology is displayed through this truth table. Let us have a look as how we can display a contradictory statement. That is, a statement is contradictory if the column under its main connective is false on every row of a complete truth table. Now consider it is raining and it is not raining, which is symbolized as P conjunction negation Q. Here the contradiction is displayed through the truth table. A statement is contingent if it is neither a tautology nor a contradiction. That if it has T on at least one row and F on at least one row. So here the truth table for implication is given. Now here
we can just have a look at what is a biconditional. The symbol tribar stands for material equivalence or biconditional. Biconditional is a compound proposition in which symbol statements are connected with phrase if and only if. When truth value of two statement is the same, then the statement is said to have material equivalence. So two statements are said to be logically equivalent when the biconditional that expresses their material equivalence is a tautology. So the following truth table displays the biconditional. Now here we can check whether two statements are logically equivalent or not. That is, P implies Q is logically equivalent to negation Q implies negation P, and the truth table for it is given here. That is, as done before, we have drawn a truth table, and we have checked all the substitution instances and found that the above statements are logically equivalent. Unit 3, methods of deduction, formal proofs of validity. So it is not always possible to use truth tables to find the validity when the arguments contain more than 3 different symbol statements. So another method is to deduce the conclusion from the premises by sequence of shorter elementary statements that are known to be valid. The premises and statements are listed as proofs of validity in one column, and justification for the latter is written in adjacent to it. The rule of inference and previous statement by which the statement in question is deduced is mentioned as justification. So we will understand in the coming sections that how we prove using the formal proof of validity. So here what we do is deduce conclusion from premises which we already know to be valid. The formal proof of validity of a given argument is defined to be a sequence of statements, each of which is either a premise of that argument or follows the preceding statements by an elementary valid argument, and such the last statement in the sequence is the conclusion of the argument whose validity is being proved. So let's check. First of all, we have to be thorough about the 9 rules of inference. The first one is modus ponens. That is, these are the elementary argument forms which are known to be valid. That is, P modus ponens, P implies Q, P, therefore Q. Modus tollens, P implies Q, negation Q, therefore negation P. Hypothetical syllogism, P implies Q, Q implies R, therefore P implies R. Next, disjunctive syllogism, that is P or Q, negation P, therefore Q. The next, constructive dilemma, that is P implies Q, conjunction R implies S, P or R, therefore Q or S. And the next one is destructive dilemma, that is P implies Q, conjunction R implies S, negation Q or negation S. We get therefore negation P or negation R. Simplification, P conjunction Q, therefore P. Conjunction P Q, therefore P dot Q. Addition P, therefore P or Q. Now there is a problem given over here, that is M implication negation N conjunction negation O implication P. Therefore M implication negation N. So the premise is first one, M implication negation N conjunction negation O implication P. So how can we derive the M implication negation N? So we can check with the 9 rules of inference and find that by using the rule of simplification we can derive this answer. And the next one,
similarly we can we can find that the rule constructive dilemma is used here in the second one to get the answer negation C or negation E. Construct the formal proof of validity for each of the following. So here the first time that we are going to prove a argument of the form given below, that is P implies Q, R implies S, negation Q or negation S, conjunction negation P or negation Q. The answer is therefore negation P or negation R. So first of all we have to look at the what is the conclusion given down here, that is negation P or negation R. So how can we derive from the given premises the conclusion? So for that we have to remember the 9 rules of inference. Which rule we should first apply? So first of all we have to put the index, that is first statement given is 1, second is given as 2, the third is given as 3, and the conclusion need not be numbered. First of all, the first step that we do is first of all we should think what answer we should get, that is the answer we should get is negation P or negation R. For that we should have in our mind which rules of inference will help us in getting the answer. So here first what I have done is the first and second statements is added or conjunction, that is 1-2 conjunction. So we can then simplify the third statement, that is negation Q or negation S. From that what we infer is that it is of the form. We should check with the 9 rules of inference which we should be thorough about and which rule it is similar to. So from this we can find that it is similar to the destructive dilemma. So we can write 4-5 destructive dilemma. So we have already found the answer. In 2 simple steps we have got the answer. If it was a truth table, the truth table will have to be will have to use how many variables, that is there is P, Q, there is R, S. So it will be very large and the procedure will be very difficult. So using the elementary valid argument forms we can easily prove that the validity of this argument. Now coming to other than the 9 rules of inference, there is rules of replacement that also which we should keep in mind. That is there are rules of replacement like De Morgan's theorem, in which we can replace negation P conjunction Q with negation P or negation Q. Similarly, we can replace negation P or Q with negation P conjunction negation Q. Similarly, there are other rules of replacement like commutation, association, distribution, double negation, transposition, material implication, material equivalence. So in order to prove the invalidity of arguments using truth table method is cumbersome. When the number of rows listed may get large, the truth table method is mechanical. While to prove the validity of arguments using the 19 rules of inference, questions like where to begin and the way to proceed needs to get solved. Here, though it is not a mechanical method like truth table, formal proof of validity is much easier than to write truth tables with many columns and rows. The difference between the first 9 rules of inference and the rules of replacement is that
rules of replacement can be applied to whole of lines or part of lines. Not only P implies Q can be replaced as negation P or Q. So here two problems are given, and one have to state the rules by which the conclusion follows from the premises. So here the rules of replacement is applied. So for the first one is A implies negation of B or negation C. So for solving this, we have to have in mind the rules of replacement in our mind. That is, which rule to apply. Here we can find that A implies negation B or negation C. The bracket can be opened, which means we are applying the De Morgan's theorem. When the bracket is opened, automatically the disjunction is converted to a conjunction, and the negation is applied to C. So in the second problem, that is G dot H implies in brackets I dot again bracket in another bracket J dot K conjunction L, the bracket close, then another bracket close. So here which we should be this is also you have to think which rules of replacement is to be applied, and we can find that in order to get the solution, that is how in the conclusion instead of J dot K it has become K dot J, and which rule we have to apply. That is, we can apply the rules of commutation. Now coming to I'm working out a formal proof of validity which carries both the rules of inference and the rules of replacement by using the rules of inference and rules of replacement. So first of all, we have to go through the premises. That is, first of all, A implies B implies C, and B implies C is in bracket, and C implies negation C. D implies A conjunction, E implies B, therefore D implies negation E. So we have to look what is the first of all we have to look what is the conclusion, and our intention is to derive the conclusion using the rules of inference and the rules of replacement. So first of all, first we have to do is we have to index, that is the first premise is numbered 1, the second premise is numbered 2, and the third is numbered 3, and the conclusion there is no numbering. So the first we have to check many possibilities which rules we can apply. So first I am here applying the A implies B implies C. We can use the rules of replacement, that is exportation. That is, when we apply the rule of replacement exportation, it becomes A conjunction B implies C. Then next again I am applying a rule of replacement, that is I am applying the material implication. That is, for the second premise I am applying material implication. Then what it will become? It was initially C implies negation C will become negation C or negation C. It means we can say that it is a tautology. That is, we can write in again we are using the rules of replacement. In place of negation C or negation C, we can write negation C as a tautology, and writing 5 tautology and numbering it as 6. Then again now we have to again check for any derivation from the above statements. That is, is there any possibility for any derivation? So first we are looking to the statements 6 and 4, and we can find that it has a status of argument form of modest tolerance, and then we apply when we apply the modest tolerance, we will get negation A dot B, which is 4 6 modest tolerance, and number it as 7. Then again we are applying, after that we apply the law of De Morgan's law. and write 7 De Morgan and write and number it as 8. That is negation A or negation B. Then next we are checking for any other derivation that is possible. That is, we have found that there is a negation A or negation B, and we check the third statement and it resembles a destructive dilemma. So we will derive, that is negation D or negation E, that is 3A destructive dilemma, and number it as 9. Hence what we get the answer is D implies negation E. That is, again we use the rule of replacement. 9 material implication. Hence we get the answer.
Construct formal proofs of validity of the following arguments with the suggested notation. So statement is given here. That is, either the mayor and the councillor will both run for re-election, or the primary race will be wide open and the party will be torn by dissension. The mayor will not run for re-election, therefore the party will be torn by dissension. So the alphabets for symbolization is M, C, W, D. That is, first statement we have symbolized is that M dot C or W dot D, and the second statement by negation M, and therefore D. So now we have to use the rules of inference and rules of replacement. Now first I have numbered it as the initial premise as 1, the second premise as 2, and I am taking the second premise M, and using the rule of addition I am adding it with negation C. Now I am applying the De Morgan. That is, by applying the De Morgan and taking the negation outside the bracket. So I get M negation of M dot C, and write it as 3 De Morgan 4. Number it as 4. Now I am trying to derive if any type of derivation is checking for any type of derivation whether it is possible. So I have checked the first and the fourth premise and found that it is a distinctive syllogism can be applied here. That is, 1 for distinctive syllogism we get W dot D and number it as 5. And after that I have used the fifth statement. I have used the rule of commutation and written as D dot W and numbered it as 6. Then again I have simplified the sixth statement using the rule of simplification, and hence I get the answer D. So I am trying to solve an argument. That is, I am trying to find the proof of an argument using the conditional proof. Here the first premise I have numbered it as 1, the second is numbered as 2, and here there is a difference in the sense I have used the conditional proof. Then here H is numbered 3, so therefore M, and in the bracket I have written it as conditional proof. So I have to get the answer M derived from all these premises. So first I have used the rule of addition and written as H or I. Then I have written it as 3 addition, then I numbered it as 4. Now I am checking for any derivation whether it is possible, and found that 1 and 4, that is it is a modus ponens, hence I can derive J dot K. Then as I have derived J dot K, then again I have used commutation, the rule of commutation, and written it as K dot J. that is, and numbered it as 6. Then I have simplified and numbered it as 7. Then I have added k with L. Then we can look for any derivation possible, and hence there is a derivation possible. Hence the statement 2 and the statement 8, it is of the form of modus ponens. So hence I get the answer M, which is the required answer. Hence we can write 2, 8 modus ponens. Hence it proves the validity of the above argument. Now coming to strengthened rule of conditional proof. In order to strengthen the rule of conditional proof for situations in which the conclusion is not explicit, conditional, thus providing wider applicability, a new method of writing proofs is used using conditional methods. Earlier we used proof as a method for proving the validity of arguments in which conclusion, which is the conditional statement, the antecedent of the condition is made the premise as an assumption, then reducing the conditional's consequent. So here instead of there is a arrow that is drawn to mark the scope of an assumption. When an assumption is made in the conditional proof of validity, scope is limited, not extending to the end of the argument. In order to mark the scope of the assumption, a new method, a bent arrow, is used. Head of the arrow pointing to the assumption from the left, and the shaft run down all along till the scope of the assumption bending inwards, marking the end of scope. So we will see how the bent arrow is used in the following argument. Just like the previous arguments that in which we have proved the validity, almost the method there is a change in that we are introducing a bent arrow, and also there is an assumption that is being made. Here let us solve this argument. Here the first premise I have numbered it as 1, the second premise L which has numbered it as 2. Now here first I have used the rule of addition, that is to the second statement, and so it has become L or M. So it is an addition and written as 2 addition. Now I will look for whether any derivation is possible, and I have found that 1 and 3 modus ponens is possible, and I numbered it as 4. Hence I get the answer N or O implies P. So now next another assumption is made, N conjunction O, and which I have numbered it as 5. Then I have simplified N conjunction O and written as N and numbered it as 6. Then an addition is made at N or O. Then I am looking for further derivation whether it is possible. Then I have found that the 4, 7 modus ponens. Hence I get the answer P and numbered it as 8. So now we can close the scope. Hence I get the answer N conjunction O implies P. The answer which we have to derive is L implies N conjunction O implies P. So from this, when we end the scope, we get the answer L. L implies N conjunction O implies P, which is 2, 9 conditional proposition, and marked it as 10. Hence we have proved the following argument using the method of strengthened rule of conditional proof. So here when the scope of an assumption ends, then the assumption is said to be discharged. So justification of reference to the assumption belongs only to the line between the limited scope and the line that discharges it.
Now next, rule of indirect proof. In the indirect proof of validity, an argument is constructed where the negation of the conclusion is assumed as an additional premise and deriving explicit contradiction from the augmented set of premises. This method is also called the method of proof by reductio ad absurdum. In elementary geometry, where the opposite of what one wants to prove is assumed. If that assumption leads to contradiction, then the theorem that we wanted to prove is true. Arguments having tautology as conclusion can be verified using truth table method. If the tautology's conclusion of an argument is not a conditional statement and the premises are consistent with each other and quite relevant to the conclusion, then argument cannot be proved valid using the usual methods, for which indirect proofs need to be used. So here why indirect, in certain situations we require indirect proofs is being mentioned. That is, if the tautologist's conclusion of an argument is not a conditional statement and the premises are consistent with each other and quite irrelevant to the conclusion, then the argument cannot be proved valid using the usual methods, for which indirect proofs need to be used. So let us check how we can prove using the method of indirect proof. So there are three premises given and a conclusion. So we have to prove that negation of A or C is valid or true. So negation of A or C is true. In order to that, I have to apply the indirect proof. In the method of indirect proof, I am again negating the conclusion. Then it will become A or C, and I have numbered it as 4. From next, what I am going to do is I am applying rules of inference, and I have found that the first statement and the fourth statement has a relation of constructive dilemma from which I can derive B or D. So hence I have derived B or D and written it as 1 for constructive dilemma and written it as numbered it as 5. Now next I have found that there is a further derivation possible in 2 and 5, that is which is modus ponens. Then I'll get E and written it as 2, 5 modus ponens as numbered it as 6. So again there is a rule of rule which can be applied, that is 3 and 6 can be conjuncted. Hence I get negation E conjunction E, which means it is a contradiction, and it has numbered it as 7. So hence we can find that the argument is valid. Logical techniques developed earlier apply only to arguments whose validity depends upon the way in which simple statements are truth functionally combined to compound statements. So these techniques cannot be applied to arguments like all humans are mortal, Aristotle is a human, therefore Aristotle is mortal. So for getting the validity of such an argument depends upon the inner logical structure of the non-compound statement it contains. So for that we need methods for analyzing non-compound statements. So we need to symbolize their inner structure. And another thing that we should remind is that attributes can not only be adjectives, it can be nouns or verbs. Singular propositions are symbolized using the alphabets, small alphabets A through W, using the first letter of the individual's name to denote that individual, and it is called individual constants.
And if in the above argument we can symbolize mortal by the capital letter M and humans by the capital letter H, the predicate term is written left to the subject term. Aristotle's human can be symbolized as big H followed by a small a, and Aristotle is mortal as mortal writing M first and a small letter a. So similarly, if we have to write Socrates is human, it will be like H and small s. Bacon is human, then H by H and small b. Spinoza is human, then H followed by small s. All these propositions have attribute symbol H followed by an individual constant. And we can write a pattern common to all singular propositions, which is known as Hx. That is where Hx is called a propositional function, where x is called the individual variable. So Hx can neither be true nor false. But when an individual, when the individual variable in Hx is replaced by an individual constant like Hs, they become individual propositions. Given any x, if x is mortal, then can be x is written as a universal quantifier. Here it can be symbolized as x in brackets mx. We can paraphrase something is mortal as there is at least one x such that it is mx. There is one x such that it is symbolized using existential quantifier, using a symbol, using a special symbol. So the above proposition can be symbolized as existential quantifier x then mx. So a general proposition is formed when either a universal or existential quantifier is placed before the propositional function. Here the existential quantification of the propositional function is true if at least one substitution instance of the propositional function is true. For universal quantification to be true, all of its substitution instances need to be true. The symbolization of nothing is mortal is using the universal quantifier x followed by negation mx, and something is not mortally symbolized as existential x followed by negation mx. We can use the Greek symbol phi. Then by using this Greek symbol we can represent the relation between existential and universal generalization using the square array. From this square array we can find that the top two propositions are contraries, which means both can be false but both cannot be true, while for the two propositions at the bottom both can be true but both cannot be false. For the proposition on the sides, the lower proposition is implied by the proposition above it. Regarding the opposite corners, they are called contradictories. So there are four types of subject predicate propositions as in traditional logic, that is A, E, I, O. That is universal affirmative, universal negative, particular affirmative and particular negative. So all the forms are given here, that is all humans are mortal, no humans are mortal, some humans are mortal, some humans are not mortal.
So we can, if we symbolize it using propositional functions and quantifier, let's first symbolize the a proposition. Given any individual thing, whatever, if it is human, then it is mortal. So we can write it as, given any x, if x is human, then x is mortal, as x universal generalization x quantifier x, and in brackets hx implies mx. So actually the a proposition is the universal quantification of the complex propositional function hx implies mx. Here we have to think that this here the substitution instances are not singular propositions, but actually they are conditionals whose antecedents and consequents are singular propositions that have same subject terms. Among the substitution instance of the propositional function hx implies mx are conditionals like HA implies MA or HB implies MB. Likewise, we can give different names. In symbolizing a proposition, the parenthesis serve as a punctuation mark to indicate that the universal quantifier x applies to its scope, the whole of the complex propositional function. Hx implies mx. That is, it is very important to understand the scope of the quantifier. So using the Greek alphabets phi and psi, we represent the attributes. Then the four general subject predicate propositions of traditional logic can be represented in the following square array as depicted here. So we can apply these quantification rules for symbolizing the following statements, like all members are either artists or engineers, which can be symbolized as x in brackets mx implies ax or ex, closing bracket twice. So again, some students are either intelligent or hardworking can be symbolized as existential x opening bracket sx conjunction ix or hx bracket close, again bracket close. So these are the way through which we symbolize these statements. Iron and copper are metals, so universal quantifier x, and in brackets ix implies mx conjunction universal quantifier x, and in brackets cx implies mx bracket close. So in order to construct a formal proofs of validity for arguments symbolized by means of quantifiers and propositional functions, there is a need for a list of rules of inference. So there are four rules being added. That is, the first one is universal instantiation, which is given below. When we use these rules to solve the arguments validity, to prove the validity. If all substitute in universal instantiation means if all the substitution instance of a propositional function is true, then the universal quantification of the propositional function is true. The principle that inference from universal quantification can result in valid substitution instance of the propositional function can be listed as a rule of inference. It
It is called the principle of universal instantiation. It is abbreviated as UI. And the symbolize. So coming to universal generalization, if K is an arbitrary selected individual, then the special attribute of K that can be generalized. What is it that makes true of the arbitrary selected individual is true of other individuals? In universal instantiation, phi K follows validly from a universal quantifier x, phi x. It means that what is true of all individuals is true of an arbitrary individual K. It can also be true in the reverse order. What is true of arbitrary individual can be true of all individuals. So here it is expressed as phi K, therefore universal quantifier x, phi x. Now coming to existential generalization, it states that if and only if there exists one true substitution instance in the propositional function, then only existential quantification of the propositional function is true. Then it can be added to the list of rules of inference. The principle that existential quantification of the propositional function can be validly inferred from any substitution instance of the propositional function. This rule allows inference of general propositions that are existentially quantified. It is called the principle of existential generalization. It is symbolized below. The fourth rule is existential instantiation. The existential quantification of a propositional function asserts that there exists at least one individual, the substitution of whose name for the variable x in that proposition function will yield a substitution instance of it. That is, here we use any individual constant which has no prior occurrence. Knowing that there is an individual which has no prior occurrence, having agreed to denote it by a symbol. So it is given below. The symbolic expression is given below. So using the new quantification rules, we can prove the following validity of the following argument, that which is symbolized as like x universal quantifier x, cx implies fx, and marked it as the first premise, existential x, vx conjunction cx as the second premise, and therefore existential x, vx conjunction fx. So the first step here it is that is used is the existential instantiation of the from two existential instantiation we will get VW conjunction CW, and we mark it as 3, and after that CW implies FW, that is it is actually one universal instantiation, and we mark it as 4. Then CW conjunction VW, it is 3 commutation, and we mark it as 5. Then we simplify and we get CW and mark it as 6. Then we get FW, that is 4 6 modus ponens, and mark it as 7. Then we again get VW, that is 3 simplification, and mark it as 8. And finally there is a conjunction VW conjunction FW, that is 8 7 conjunction, and mark it as 9. And finally hence we have from the 9th step we can infer that is it is an 9 existential generalization. We get that existential x, vx conjunction fx, and mark it as 10, which is the answer. Thank you.